When a new AI model drops, engineers focus on GPU throughput and parameter counts. They assume time is just a background number ticking away safely in the corner of their logs. But what happens when that clock ticks backward, or skips forward by an hour instead of a second? The current debate among timekeepers about adding leap seconds or even considering a full leap hour reveals something engineers rarely talk about. Your distributed AI infrastructure has a single point of failure built right into its foundation. It is not the model weights or the data quality. It is how we handle nonlinear time in systems that demand perfect order. Today, we connect this headline to the engineering reality of modern machine learning pipelines. We are going to look at why treating the wall clock as a passive utility is an existential risk for any team running distributed training or real-time inference. You might think your system can survive a glitchy second, but what happens when that anomaly grows into a minute, or worse, an hour? The stakes here go far beyond fixing a timestamp error in a log file. We are talking about the fundamental consistency of vector databases, reinforcement learning state tracking, and the consensus protocols that keep thousands of GPUs working together without corrupting data. The core issue stems from a mismatch between physics and computer science. For decades, we have relied on coordinated universal time to align our digital clocks with the Earth's rotation. But the planet is slowing down due to tidal friction, requiring these occasional adjustments known as leap seconds. Computer systems, however, are built on linear logic. They assume that time always moves forward in a straight line. Time TP sect, TP sect, TP sect must be greater than time. This assumption is baked into every major distributed consensus algorithm used by tools like Kubernetes, Spark, and Ray to orchestrate AI workloads. When the Earth slows down or speeds up just enough to trigger an adjustment, that linear logic breaks. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider what happens during a standard leap second insertion. The system sees a duplicate timestamp where two distinct events happen at exactly the same moment in wall clock time. In a vector database used for embedding similarity searches, this causes collisions. A new state might overwrite an old one because they share the exact same index key derived from that duplicated timestamp. Or worse, the indexing logic fails to store either record correctly. For teams running reinforcement learning agents, which rely heavily on precise temporal ordering of rewards and states, a single duplicate timestamp can cause the agent's internal model of the world to diverge completely. The data becomes garbage, but it is hard to debug because there are no error messages at the application layer. Now imagine we scale this up from 1 second to something much larger. Timekeepers have discussed the theoretical possibility of a leap hour if Earth's rotation slows significantly further in the coming decades. While most teams are currently patching their systems with leap smearing techniques that spread the adjustment over several hours, these software patches introduce latency jitter and complexity they were not designed to handle at scale. If your infrastructure is built to absorb a 1-second anomaly but faces an hour-long nonlinearity in time, it will fail catastrophically. The retry loops inherent in consensus protocols like Raft or Paxos would trigger infinite cycles as nodes struggle to agree on who leads the cluster when their internal clocks are out of sync by minutes rather than microseconds. This brings us to a critical realization for senior engineers. We have been treating time synchronization as a trivial system variable, but it is actually an active failure mode that can cascade from a single timestamp collision into total pipeline corruption. The industry is currently moving toward a trade-off, where teams must decide whether to decouple physical time entirely or accept higher latency costs during anomalies. This decision impacts every layer of your stack, from the streaming frameworks you choose for real-time data ingestion to the specific databases used for storing model states and logs. The engineering fix requires abandoning the reliance on wall clock timestamps for state consistency within distributed AI systems. Instead, practitioners must adopt logical clocks or hybrid logical clocks that track causality rather than physical seconds. These internal counters ensure that even if the external clock jumps forward by an hour, your system maintains a consistent ordering of events based on what actually happened in the cluster, not what the calendar says. This shift is essential for reliability because it means your AI training loops and inference pipelines can survive any nonlinear drift without data loss or model corruption. We are building systems to handle 1-second anomalies with smearing patches, but our architecture remains fundamentally brittle against larger nonlinear time shifts like a potential leap hour. If you audit your current pipeline today and find that it relies on get time of day for critical state management rather than logical timestamps, you have not designed for reliability, you have designed for luck. The next generation of robust AI infrastructure will treat the clock as an artificial construct to be managed by internal logic, ensuring that no matter how the Earth rotates, your models keep learning and inferencing without a glitch. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.